Do you see the
We see
slide?
it.
На каком месте я ушел?
В самом начале.
В самом начале, да? А? Так, сейчас я
Please excuse us for some technical difficulties. Now the speaker will continue.
Okay, so I can start again because I started not knowing that you do not hear me. Well, this is a kind of presentation which is different from what we have before because I decided that sometimes we have to ease our life and not to concentrate on formulas. Moreover, that relativity is well known to every in this audience. They use it in their everyday work, so I will not dwell upon the relativity formulas and so on, because everybody knows that. So instead of this, I will concentrate on some moments of the history of creation theory, and I will limit myself mostly, again, not with formulas. Sometimes I will give them, but not very often, but by citation from those who took part in the creation of this theory. And the conclusions you may do yourself, because you will see just the citation with that. I will not add myself something to that. The first one certainly is Galileo Galilei with his principle of relativity. Certainly you can find in literature that even ancient Greeks also introduced some notions, but it was made in so vague form that I considered it better not to show them at all. Concerning this principle of relativity, which is written here, this citation from the famous book Dialogue, which was written, as we know, in the 30s of 17th century, it is written how Galileo Galilei understood what we call now the relativity principle. You may very often meet that statement that Galileo, he had in mind some limited principle which also only concerned the mechanical movements. That's what we should not be agreed with that, because he mentioned here every and all physical phenomena he knew that time. He did not exclude, for example, gravity, because he argued about the falling down things inside the street and so on. And so this point of view that he was limited with only mechanical movements is absolutely wrong. So this principle is given here in full generality. And I believe that we should credit Galileo Galilei as the man who, for the first time, gave us this principle in its completeness. Now, after that, certainly we have to, it doesn't work. Now, certainly everybody after Galileo mentioned Isaac Newton, and I just have taken a very simple quotation from him, because he thought about, he was the author of a very nice theory, but it was the force at distance. The force at distance is difficult to understand, how bodies can feel each other through the empty space. And so that was a subject of thinking. But here I want to mention what Professor Zakharov said me today, that certainly before Newton, I should always remember about Johann Kepler, who had many influences to thoughts and deeds of Newton. So we give him certainly credit, and go further with Newton. Concerning the what is in this empty space, he did not make any hypothesis. You all know his famous sayings about he doesn't invent the hypothesis and all that. So let's go further. before him, before even when Newton asked himself this question, it was already answered by René Descartes. And this is a person to whom people, normally historians and physicists, prescribe the first use of the term the ether in its physical significance. Then, when the ether was already the part of physical understanding of the propagation of electromagnetic waves, because to have waves at that time people thought, and it was a reason for them, that if you have some waves, or the waves on the water, you have something which should bear these waves, and where they should propagate as perturbation of this medium. And this medium is this famous ether. And one of the first people who thought about the how to say effects of this ether on observable phenomena was Maxwell, and he was the first who posed such a question just 1 year before his death about the possible experiments to try to measure the velocity under the world ether. It means that the velocity of our movement through the absolute space. Now, this person I show here, it is absolutely unknown to even to those who are interested in the history of physics. And this is Professor Eleuthère Mascart, or as French people say, Macquart, who was a very known optical physicist, and he provided experiments to try to find the manifestation of the absolute movement with use of optical phenomena like aberration and refraction of light in crystals and so on. Many experiments. He wrote huge review article in '72 about his experiments, and here there is a conclusion of his works. If you take the last words here, this phenomena, he means under phenomena, he means the science of the moves through the absolute space, do not give any means of measuring the absolute motion of a body, and that relative moments are the only we can measure. So we can only perceive relative movements, not the absolute ones. And he is mentioned very rarely. I don't know why, because only in one book devoted to the history of relativity I could find his name and then find the article he wrote about this. Eleuthère Mascart. So actually here we see that his formulation of his conclusion is very close to the relativity principle as we know it now. But nonetheless, he was not credited for his breakthrough, I believe. So in spite of his experiments, so the other people tried to continue that in different ways. I don't want to draw you the installation of microphone to measure the ether or the ether wind. And first he tried to do the experiment himself. Then he invited Morley, and finally they made the famous experiment where the conclusion was, if you will read the paper by Michelson and Morley, the conclusion is not very conclusive, but nonetheless it was said clearly that the Lorentz theory is false, it failed. What is the Lorentz? The Lorentz theory certainly was based on the notion of the immovable ether, and the wind should be seen, but it was not. It was not. It was a discussion. Here also in the paper, they described other experiments which are to be provided. And several years after them, and several tens of years, people emphatically tried to measure and measure again in order to try to find out the manifestation of the movement through the ether. All results are were and are negative. So what does it mean? That if even the ether exists, it resists to its manifestation. And here I show you the Vladimir, the professor from Göttingen, who investigated the transformation which left the wave equation intact, invariant. And he has found the transformations which is written here. Look at them, and you easily see that they are very much remind what we know under the Lorentz transformation, except that factors which are stated here, they preclude to this transformation to form a group. This transformation do not form a group. But nonetheless, already from this transformation, we can learn many interesting things. What I want to draw your attention to is the introduction of this new time, T prime, which was later called for some time the local time. But actually, as was explained later, not by him, but by Poincaré, that this time is a genuine physical time, but just in the moving frame. And from this formula, you can also, it's not difficult to derive many things which are known now. For example, the relativistic addition rule can be obtained from this formula, and so on and so on. But as always, or almost always happened with the heroes of our story, he was put in oblivion, and only 3 years ago, Lorentz remembered or have found in literature this reference to this paper and made this reference. Now, Heaviside, you know that this is a very peculiar person. There is many books about him. Very special man. He was at the same time not only a scientist, a physicist, but engineer and so on. And actually, he has written the paper in 1999, where he investigated the form, the shape of the field around the moving charge. And he has found that this shape should be ellipsoidal. So there is a kind of contraction in the direction of movement. The next person is Fitzgerald, who was a friend of him. They were friends, actually, and he written the very small. It's not even article, just several sentences in the newspaper that all bodies, in particular the road, should contract in the. And his argument was very simple, because that time, it's true now also, we know that bodies, they consist of constituents which are kept together with electromagnetic forces. If they are kept together with electromagnetic forces, certainly, and if the fields are contracted, so the very bodies also should be contracted. The very natural thought about that. Now, Joseph Larmor, he has written in 1900, in 1889 was written the last paper. He was a part of this book, or his book, which was written in 1900, the book devoted to the ether and its manifestation. And actually, the constituents of what we call now the relativity theory can be found. So not without some labor, it's not very easy to read the paper, but some interesting things you can find. For example, the dilation of time. the individual electron described corresponding parts of their orbits in time shorter than for the rest system. Then you can find even in this paper these transformations. Certainly in this paper they were not given in this final form, but they were presented by two steps. First, he made transformation with help of what we call Galilei transformation, and then the second step brought him to these transformations, which we used to call Lorentz transformation. But actually, if to be fair and just, we have to call, why not to call them Lamont transformation? But nobody does that. Then, finally, Lorentz. Lorentz was very much known at the time, I mean, in the end of 19th century, the beginning of the 20th century, because he wrote, he created a theory, the theory of electrons, which was considered as a theory of matter at that time. And he describes an enormous number of physical effects, Zeeman effects, etc., except maybe those who were related to the movement of bodies. He tried emphatically to try to reconcile the absence of the ether wind with his transformation, and he did that actually in this paper, and in this paper also he was considered as the top of his creativity. And in this paper, the transformations which we have seen just now were also formulated. Transformation of electromagnetic fields with some mistakes which were corrected afterward by Poincaré. And here is the Poincaré. Poincaré considered from the very beginning some interesting subjects which were not in the habit to discuss among physicists at that time. For example, the relativity of simultaneity. And he wrote a not very big, not very large paper, La mesure de temps, the measure of time, where he provided the procedure of synchronization of clocks with help of sending light signals forth and back. And in this paper, for the first time, he put his attention to the fact that light has a constant velocity, in particular that velocity is the same in all directions. This is what later we'll see will be what was called by Einstein the postulate of the constancy of the speed of light. But for Poincaré, this consideration, this thought was not very important, because actually you cannot even find in his afterward writings. What you can find, that there is a formulation of this point 1, 2, 3 in his book Science and Hypothesis. And the book is very popular, and I think that some of you have read it, and this is not really interesting book, Science and Hypothesis. And okay, you see that already in 1902 he has formulated what we can call rightly as a relativity principle. And you see that in this formulation of the relativity principle, he doesn't even mention the constancy of the velocity of light to such an extent that in his writings about that, he always has chosen units where c equal to 1. This is a sign. And the papers which are considered as final formulation of the relativity theory, not only principle, but also equations of fields, equation of relativistic mechanics, were done in these two papers. The first paper was presented to the French Academy of Sciences, and it is short but contains all the essential results. The second one was sent to Italian mathematical journal, Rendi Conti di Palermo Matematico, something I don't know how to call them, where at a very long, you can find there the presentation of the very essential equations of what we call now relativity theory, including the generalization, relativistic generalization of the action principle and derivation equations from this action principle, and many other things. Okay, but now let me add to this, not him, let me add to this, and trying to continue the line setting of Soviet comedy films, а не замахнуться ли нам на Альберта нашего Эйнштейна. Here you see that, I don't know how many of you tried to read the original paper by Einstein. Personally, to me, it was not very easy reading anyway, but it doesn't mean that it's bad article. But what is clearly said in this article is that, first of all, this is almost the same what was said in the formulation of the relativity principle by Poincaré. But the second point is exactly the postulate of the constancy of the velocity of light. Well, but after that, the German mathematician Minkowski, he made his speech before the Congress of German mathematicians, physicists, and even mathematics, with this speech where he made very big, very large progress in formulation of the relativity principle, in which we use up to now, because it was him who introduced terms like light cone, forward light cone, backward light cone, 4-vector, and time-like vector, space-like vector, and he also formulated the relativity principle in the tensor form, what now is used very much, and was very helpful for further investigation in the presentation. Well, now when we have seen the citation from people who took part in the creation of what we call now the relativity theory, the resume of this activity was expressed by the famous mathematician Hermann Weyl in such a way that the foundation and creation of the theory of relativity is the work of one single person, Albert Einstein. Certainly, we see there's some dissonance with what we have seen before. So certainly, not only the only person, in spite of in his original paper, I mean Einstein, you will not find a reference to other people, not to say about Poincaré, but he mentioned only Maxwell in his paper and Newton maybe. That's all. Though certainly there's clear indication that he wanted to be among really big people. He did not pay much attention to his contemporaries who also worked on the subject. Okay, but it's up to him. Now there is another citation from Poincaré concerning this one. I don't want to read you, okay, you can do that. The sense is, the meaning of this citation is that contrary to the opinion of another mathematician, while Poincaré, great not only mathematician, but also philosopher and a physicist and engineer and everything, his opinion was written here, and I think it is much more true, much more fair to people who work in science. And this is reflects two points of view. One point of view is there is one giant, and Albert Einstein, and the second point is that the actual relativity is the result of the labor of many contributors. Now let's take the principle of relativity, constancy of the velocity of light. I want to concentrate a little bit on the constancy of light, and it was put into doubt by our compatriot Vladimir Sergeyevich, a very interesting person, who in December of 1909 in the Congress of Russian scientists, medicine, physicists, and so on, he made the report concerning relativity principle. Then he left to Germany, where he worked. And finally, you see that he started exclusively from the relativity principle. No light, no other peculiar special interactions of children. Only the relativity principle and reasoning with the use of isotropy and homogeneity of space, and the group character of transformations which corroborate with the relativity principle. Here you see the Minkowski transformation. In his reasoning, after all, there was shown that there exists, he called this the gold constant, some constant of this dimensionality, 1 over velocity squared. And actually the sense of this constant was not the light velocity. Even without light, it exists. It is just a limiting velocity above which no one signal can be transmitted. And I think, to my mind, that up to now, for example, if you take the popular or the textbooks, that very often people continue to present relativity principle as first the very relative principle, and then they add, invariably, they add the principle of the constancy of light, of the constancy of the velocity of light. But this is a consequence of this relativity principle. Certainly, I don't think it's very harmful to add to the principle its consequence. I don't think that's something bad, but it's not logical. And also, what is the achievement, the main achievement of Ignatowski, that he, for the first time, not relying on any specific interaction or form of matter, formulated consistently what we have to call now the relativity principle and the relativity principle. I'd like to say that it's repeated that the modern textbooks do not take into account. He is not known in our country. I already said before that in 1941 he was arrested by the security forces, and he was blamed falsely that he was presumably German spy, because he spoke German very nice. And actually, several months since his arrest, he was sentenced and just executed. This is it's very pity. I don't know why. In our even for example, in Russian physical literature, we have no translation, Russian translation of his works. I think it's not very good, so we should do that. Okay. So I give him the full tribute, and I think that we should do everything to reinstall his name in the history of relativity. Now, on the limiting velocity, actually people very often, also in textbooks, you can find the mixture of notions, and very often people may make wrong conclusion because they are not aware that the physical velocity is given by this formula, but instead of they use coordinate formula, the coordinate speed of light may take any value from 0 to infinity. And to this we are off, namely to Ignatowski. In spite of, certainly he did not use this apparatus of tensor calculus, but nonetheless the essence of what he has done is expressed namely this formulas. Okay, now the ether. The first ether was rejected by Einstein. It was written, no, we have no need in this medium. But then, 15 years since then, he was back to that, and he said that certainly it is absurd to imagine the empty space. The empty space is absurd. It's something which is not. Though people knew that before many times. But he understood under the ether that time he understood the non-trivial metric tensor. Is a field that this is, according to him, should be considered as a new ether. But nonetheless, now there are some people. I read several papers. I don't want to take to give names of people because they say almost the same. There are proposals to consider as ether the quantum vacuum, because quantum vacuum, the properties of the ether is immovable in any inertial frame, is momentum 0. He is invariant, and it is invariant and can be used as a representative. To what extent can we imagine that the propagation of light can be considered as a perturbation of the vacuum? Certainly, you can imagine that a photon, when it moves through the physical vacuum, it can transform into, for example, electron-positron pair, then back to eta, and through the many various fluctuations, it moves through the space. But certainly, it's not the same mechanical picture as people imagined when they argued about the mechanical ether of Descartes. There are also proposals to consider CMBR as a new ether. That's also the open question. If you like, you can do it. And in some sense, it is chosen frame of reference, and certainly you may do that. Well, and I think that I don't want to make conclusions because the history is very peculiar things. Most of all, when you argue about priority, this is interminable. But what I want to say that what I try to show you contrasts very much with what we have now in literature. You may find a lot of books devoted to Einstein, very, very nicely, in very luxury envelopes and so on. And every year, almost somebody else writes down the book of which great person was Einstein and so on. They repeated some without end. Concerning the different point of view, certainly the number of books is very modest, maybe 1/10 of them, and they are not very much known to public. I don't want to say something bad in address of Einstein. Certainly, in spite of his exaggerated glorification of his name, namely this glorification propagated in the mass media attracted many young people to become physicists and to make them very good things. In particular, in this, it's certainly the good thing he done by himself. Okay, and here I think I have to stop. Concerning the question, maybe there are questions.
Thank you, Professor. So questions. One question. Okay. Georgi?
Hello, yeah. It's mostly, I would say, one question and one comment. Uh, as far as I know, there is the only one textbook which mentioned Ignatowski. Is Wolfgang Paul's famous monograph about relativity theory, right? Do you know any other who mentions him?
What? Gil, repeat, please. I didn't catch what you have said.
Sorry, sorry. As far as I know, there is only one textbook which mentions Ignatowski. It is Wolfgang Paul's famous relativity theory monography, right? Is there anything else?
Yes, that's right. In the book of the famous book written by Pauli, it was the famous relativity theory. You can find, huh? You can find in the book by Pauli the reference to Ignatowski, but the reference is made very cursorily, I would say, with negligence, with some negligence, because he said yes, he found something with okay, but certainly not compared with what Einstein did. But at the same time, Pauli recognized the role of Poincaré almost on equal foot with Einstein. But now in recent times, time after time, the papers, not Russians, unfortunately, appear where people try to rederive what Ignatowski done. It was made several times. It was published, and after that, our authors they got knowledge that it was done maybe half a century before them. Okay, so I think that we should give tribute to this great man. I mean, Ignatowski. At least if somebody will be able to help to translate his papers in which are written in German and to put place them in the Uspechy of Physical Sciences, it would be very good. Okay, thank you.
One more question.
Yes.
Yeah, so I have read the original article by Einstein, and I remember that he mentioned in the article Lorentz, but there are no there are no references to article at all. So at that time in 1900s, was it a usual thing to write an article, mention a name, but do not put a reference?
Certainly not. If you take, for example, the Poincaré papers, his papers are full of references, and very often he was a very kind person. He gives the tribute without reason to people. For example, it was him who named the group Lorentz, in spite of the transformation. The Lorentz could not prove the full invariance of the system of electromagnetic equations because transformations of currents and charge densities were done correctly, and it was Poincaré who made correct things. No, I think, to my knowledge, I have read at least some related references were always. So this is something unique what concerns Einstein, and his partisan of Einstein, they explain with many reasons why he did not mention, because he was very poor clerk in some enterprise, I don't know where, in Himalaya maybe, what. But no, on the other hand, we know that he worked in some bureau in Switzerland, which was field of technical literature. The newest articles came to this bureau almost every day, so it's not true. Certainly he was aware, but who knows? The only thing which I can say about Poincaré, about Einstein, it was Pice, his biographer. He wrote that Einstein said that he had never read the paper by Poincaré on relativity. And in 55, Pice has given to Einstein the paper by Poincaré. And Einstein was dead several times after that. And nobody after his death could find this article in his apartment. I don't know. I had even hypothesis that it was a reason for success.
Okay, thanks.
Thank you.
So no more questions. I see. Okay, due to some technical delay, the second part of the session will start at 17:30, 15 minutes later.
У нас на кофе нет, да? Сейчас нет, у нас
15 минут.
А, есть?
Нет.
А,